Hello everyone, my name is Tainan Xiao. I am now a postdoc working in the Department of Electrical Engineering, Tsinghua University. My supervisor is Professor Ying Chen. My research interests include power system stability analysis and control, high-performance computing, and artificial intelligence. On behalf of all the authors, it is my pleasure to present to you our work, named A Fully Parallel Nested BBDF Method for Power System Transient Stability Simulations. This work is a continuation of our previous studies on parallel transient stability simulations. In our previous studies, we tried to improve the traditional and widely used parallel simulation method, the BBDF method. In the BBDF method, the original network is divided into several subnets and one Carnot network. Since they form a tree-like structure, here we call the original subnet the leaf subnet, and call the Carnot network the root subnet. The workflow of the BBDF method is shown. There are still seriality in the procedures. It must be solved in this order: forward substitutions of the leaves, solution of the root, and backward substitution of the leaves. The seriality is the main theoretical issue of the BBDF method. For this issue, we proposed a fully parallel BBDF method, FNBBDF method. In this method, we perform the forward substitution of leaves and backward substitution of the root at the same time. Then we perform the backward substitution of leaves and forward substitution of the root at the same time. By doing so, the solution of all subnets are parallelized. Detailed analysis can be found in reference 1. On the other hand, parallel overhead has not been well studied in the research field of power systems. In the workflows, we can see barriers. They mean multiple threads must synchronize here. The dot-dashed boxes show the memory sharing and copying around threads. These actions will cause parallel overhead. How to reduce the parallel overhead is the implementation issue in the BBDF method. We did detailed studies and proposed a nested BBDF method based on subnet core mapping. The idea is to reasonably assign computing tasks based on network segmentation, computer structure, and a parallel communication topology. The original network is divided into 3-layer structure: leaf subnets, branch subnets, and a root subnet. Leaves and corresponding branch are bound to the CPU cores on the same CPU chip. Parallel communication between cores on the same chip is done by OpenMP, and the communication between cores on different chips are done by MPI. By doing so, the parallel overhead can be reduced. Detailed analysis can be found in reference 2. There are still problems in the existing methods. In the FNBBDF method, the root will grow larger and larger as the network are partitioned into more and more subnets. When the root subnet has the highest computational burden, the speed-up saturates. For the NBBDF method, the seriality in the solution procedures needs to be dealt with. Obviously, by combining the two existing methods, we proposed the fully parallel nested BBDF method, FNBBDF method. The idea is straightforward. The original network is partitioned into a leaf, branch, root structure. We perform the forward substitution of leaves, backward substitution of branches, and forward substitution of the root in parallel. Then we perform the backward substitutions of the leaves, forward substitution of branch, and backward substitution of the root in parallel. So all the subnets are solved in parallel. Meanwhile, the computing tasks are also bound to certain cores under the same principle. Leaves and branch are assigned to cores on the same chip. Therefore, by introducing the NBBDF method to FNBBDF method, the root subnet of the FNBBDF method is separated. By introducing the FNBBDF method to the NBBDF method, The seriality is eliminated. By utilizing the subnet core mapping, the parallel overhead is reduced. Of course, a higher speedup can be expected. However, we can also see that with the same number of CPU cores, the total number of subnets of the FNBBDF method are the smallest compared with the FBBDF method and the NBBDF method. So the subnet of the FNBBDF method tends to be larger. We can also expect that when the number of CPU cores are small, FNBBDF method will not be as effective as the other two. We implemented the FNBBDF method and compared it with the other two. The high-performance computing platform is Sugang 950G server with 8 Intel Xeon processors. Each processor is integrated with 8 CPU cores, which means there are totally 64 CPU cores. The detailed information of the 3 test systems are displayed in the table. The 2383WP system is a widely used test system in MetPower. System 1 and System 2 are 2 practical national power systems. Dynamic elements are modeled in detail. Multiple 10-second simulations are carried out. The serial timings shown in the table are the baselines for the parallel simulation tests. The program is all written by ourselves with C++. The development IDE is Qt5. The program is part of our software called Power System Optimal Parameter Selection, PSOPS for short. The software contains all our previous work. The comparative results are shown. Obviously, in all 3 test systems, the proposed FNBBDF method obtained higher speedups, especially when the number of CPU cores are large enough for the test systems. Just as we mentioned before, when the number of CPU cores are still small for the power system, the FBBDF method and the NBBDF method are more efficient. However, when the number of cores is large, the FNBBDF method always wins. The highest speedup ratios increased about 36%, 23%, and 21% in the test systems, respectively. And in System 2, the speedup ratio of the proposed method is over 21, and it has not even saturated yet. The 10-second simulation of the 24,886 node power system only takes about 0.64 seconds. To conclude, we proposed an FNBBDF method based on our previous studies. The method is suitable for large-scale power systems with large number of CPU cores. The FNBBDF method program is integrated in PSOPS. Recently, we have developed a Python API for PSOPS and published it on GitHub. We used it to generate over 50 million simulation samples of IEEE 39 system in 9 hours with 40 cores. The samples are used for our research on artificial intelligence. The API is also used to build power system environment for studies on reinforcement learning. We hope that you could also download it, use it, and give us suggestions. That's all for the presentation. Thank you for your precious time. We look forward to your valuable comments and suggestions. Thank you.